This next line of code will then create a pooling layer. It's max pooling because we're going to take the maximum value. We're saying it's a 2 by 2 pool, so for every 4 pixels, the biggest one will survive, as shown earlier. We then add another convolutional layer and another max pooling layer, so that the network can learn another set of convolutions on top of the existing one, and then again pool to reduce the size. So by the time the image gets to the flatten to go into the dense layers, it's already much smaller. It's been quartered and then quartered again, so its content has been greatly simplified. The goal being that the convolutions will filter it to the features that determine the output. A really useful method on the model is the model.summary method. This allows you to inspect the layers of the model and see the journey of the image through the convolutions. And here is the output. It's a nice table showing us the layers and some details about them, including the output shape. It's important to keep an eye on the output shape column. When you first look at this, it can be a little bit confusing and feel like a bug. After all, isn't the data 28 by 28, so why is the output 26 by 26? The key to this is remembering that the filter is a 3 by 3 filter. Consider what happens when you start scanning through an image starting on the top left. So for example, with this image of the dog on the right, you can see zoomed into the pixels at its top left corner. You can't calculate the filter for the pixel in the top left because it doesn't have any neighbors above it or to its left. In a similar fashion, the next pixel to the right won't work either because it doesn't have any neighbors above it. So logically, the first pixel that you can do calculations on is this one, because this one, of course, has all 8 neighbors that a 3 by 3 filter needs. This, when you think about it, means that you can't use a 1 pixel margin all around the image, so the output of the convolution will be 2 pixels smaller on X and 2 pixels smaller on Y. If your filter is 5 by 5 for similar reasons, your output will be 4 smaller on X and 4 smaller on Y. So that's why with a 3 by 3 filter, our output from the 28 by 28 image is now 26 by 26. We've removed that 1 pixel on X and Y in each of the borders. So next is the first of the max pooling layers. Now remember we specified it to be 2 by 2, thus turning 4 pixels into 1 and halving our X and Y. So now our output gets reduced from 26 by 26 to 13 by 13. The convolutions will then operate on that, and of course we lose the 1 pixel margin as before, so we're down to 11 by 11. Add another 2 by 2 max pooling to halve this, rounding down, and we're now down to 5 by 5 images. So now our dense neural network is the same as before, but it's being fed with 5 by 5 images instead of 28 by 28 ones. But remember, it's not just one compressed 5 by 5 image instead of the original 28 by 28. There are a number of convolutions per image that we specified, in this case 64. So there are 64 new images of 5 by 5 that are being fed in. Flatten that out, and you have 25 pixels times 64, which is 1600. So you can see that the new flattened layer has 1600 elements in it, as opposed to the 784 that you had previously. This number is impacted by the parameters that you set when defining the convolutional 2D layers. Later, when you experiment, you'll see what the impact of setting what other values for the number of convolutions will be, and in particular, you can see what happens when you're feeding less than 784 overall pixels in. Training should be faster, but is there a sweet spot where it's more accurate? Well, let's switch to the workbook and we can try it out for ourselves.